Alright, so yesterday we left off talking about the reactions that acids do. And the last type of reaction we looked at, what we'll continue to look at today, was a reaction between an acid and a base. What was the special name I had for the reaction between an acid and a base?
Neutralization.
Neutralization reactions. Let's look at a few of them. So let's say I have HNO3, AQ, plus lithium hydroxide. So is that an acid plus a base? Yeah. So what two products will I get when I have a metal hydroxide plus an acid? Water and a salt. Or you can just do double replacement. The Li and the N swap places. So I get H2O. What phase symbol does the H2O get? Liquid. Plus LiNO3, which is soluble, so it gets an AQ. Okay. So because they form liquid water, these reactions always happen. Okay. So with double replacement, we look for a solid or liquid product. We always make water with a metal hydroxide plus an acid, so they always happen. But what does an acid do when it's dissolved in water? It ionizes. What does a base do when it's dissolved in water? What does lithium nitrate do when it dissolves in water? Dissolves. So what does this ionic compound do when it dissolves? Associates. Okay. So can we write this in the expanded ionic form? Yeah. Let's go into it. H plus, AQ, nitrate, AQ, lithium. And you all know the order doesn't matter. You can scramble them around. So in the past, when I wrote the net ionic equation, I wrote the solid product plus everything I needed to make the solid product, correct? Here, do I have a solid product? No. So what product do you think I'm going to make with my net ionic equation? The liquid. So my net ionic equation is just H plus AQ plus OH minus AQ makes H2O. So if I have a metal hydroxide plus an acid, one of the products is always going to be what? Water, right? Which is the liquid. So the net ionic equation for a metal hydroxide plus an acid is always going to be that. It's always going to match that. So we could look at another one. We could look at H2SO4, which is sulfuric acid. And by the way, yesterday we reviewed naming. That should not be the hard part moving forward. Okay? The problems are going to get complicated. You have to write a reaction, then do calculations. If me saying sulfuric acid in words, and you having to think about what that means is the hard part, we're in trouble. That should be the easy part here, is naming. Plus CaOH2, which is calcium hydroxide. Go ahead and write the products, and then write the net ionic equation. You can write the ionic if you want to. I think you can all handle that at this point. You can leave the 2's or reduce the 2's in the net ionic. Either way is okay for now. Yeah. It just takes one number to balance it. So not really anything truly new. Yes.
Why are the 2's written as coefficients on that ion?
Because this H2 tells me there's 2 hydrogens. So when they ionize, the 2 hydrogens just float around separate. So it just tells me there's 2 H pluses. And somebody asked earlier, I didn't clarify this earlier, the diatomic rules do not apply to solutions. Okay, so you can have H plus just floating around. It's not going to be H2 always. Okay. Any questions about that? Good. So we said yesterday that by definition acids are proton what? Or what do acids do to protons?
Donate.
They donate protons. Okay, so acids donate protons. So that means the bases do what? Accept. Okay, so where people use protons. So if we turn over, there are a couple of the word theories used. We could say explanations or definitions of acids and bases. For this class, we're going to stick with the third one down here. Okay, then we'll just talk about 1 and 2 so you know they exist. It's the Bronsted-Lowry definition of acids and bases. Bronsted and Lowry were just people's names. And this is the definition of acids and bases we use. So if you hear the word acid or the word base used, that's referring to the Bronsted-Lowry definition. So an acid is defined as a proton donor, and a base as a proton acceptor. So what is used interchangeably with the word proton? Hydrogen ion. Okay. So hydrogen ion and a proton are the exact same thing. Those 2 words that describe the exact same molecule there, or exact same particle in the molecule. But it turns out that H pluses, when they're in water, react with water. What is the name of the product of that reaction, do you think? You know it. Name. Hydronium. So H3O plus. So I can say that this is equivalent to hydronium, as long as we're in water, which for this class we will be. So hydronium is not the exact same thing, but they're equivalent, okay? Because the hydrogen and the proton becomes hydronium when it's in water. Okay. So now we can look up at some of the other explanations or definitions that are used that we won't talk about much. The Arrhenius definition, which is another person's name, says that acids produce or increase hydronium in water. So the acid definition is pretty much the same, right? Down here we said the proton donate. Up here they say they increase hydronium. The protons and hydronium are equivalent, kind of the same thing. The difference is the base definition. The base definition says that it increases hydroxide ions. So if the base is a metal hydroxide, then that's true. But we have other bases that are not metal hydroxides that don't quite fit this definition. So I just want to make you aware of that. We won't really talk about it much. And then the last and the more modern explanation or definitions of acids and bases we call Lewis acids and Lewis bases. When have you heard the name Lewis before in chemistry? The Lewis dot structures, Lewis structures for molecules. Gilbert Lewis, the same person. This was his idea. So he said that Lewis bases do what? Donate electrons. And the Lewis acids accept electrons. Okay? So a little bit different definition that talks about electron pairs moving rather than hydrogens moving. Okay? So if you take high-level chemistry, we'll talk about that quite a bit. But for now, just be aware they exist. And we're going to focus on this area right here. Acids donate protons, bases accept protons. Okay? So, and I'm not going to write this out. You can all show the ionization of HCl and the dissociation of sodium hydroxide, right? We've done that quite a bit. So down here, we have two new words, conjugate acid and conjugate base. So let's write an example to look at what this means. So let's just write H2SO4 plus H2O makes H3O plus HSO4 negative 1. Okay, so in that example, what did H2SO4 do? It donated a hydrogen, okay? So H2SO4 gave away a hydrogen. So if it donates a hydrogen, what name does it get? Or what word describes it? It's an acid. So I can label that as an acid. So then, what did water do? We typically use the word accept, but gain and receive the same thing. It accepted the hydrogen. So what do we call that? Base. Are we all okay with labeling the acid and the base in that reaction? Okay. So now, let's look at the reverse reaction. So the reverse reaction is H3O plus HSO4 negative 1 produces H2O plus H2SO4. In that reaction, what did H3O plus do? Did it donate or accept the proton? It donated. So H3O plus gives away a proton to become water. And do we all see that? So if something gives away a proton, what name does it get? But it's in the reverse reaction, so we call that a conjugate acid. Sometimes you'll hear it described as the conjugate acid is what arises from the base, and the conjugate base arises from the acid. It's easier to think about it in terms of the reverse reaction. So in the reverse reaction, what did HSO4 negative 1 do? Accept or donate a proton? Accepts. So if it accepts, is it acid or a base? Base. So what kind of base? Conjugate. So the conjugate base. Yeah. Okay, let's look at this one. HCl plus water makes H3O plus Cl minus. What is the HCl doing? Donating or accepting a proton? Donating. So acid or base? Acid. So what is the water doing? Donating or accepting? Accepting. So what is it? Base. So acid and accepting do not go together. The A's don't correlate. So then in the reverse reaction, my arrows didn't print. They never do. What is H3O plus doing to become water again? Donating. So what is it? So acid, what kind of acid? Conjugate acid. Then if we did it right, Cl minus should be the conjugate base. Does Cl minus even have the ability to donate a hydrogen? No, so it's got to be the conjugate base. And this pattern is just a coincidence, okay? It's been acid plus base makes conjugate acid plus conjugate base. It can be flipped. I could easily flip it around and do base plus acid. There's no like pattern to memorize here. Okay. So y'all try the next one. HCl plus NH3 makes NH4 plus Cl minus. So the same pattern worked here, but it's just a coincidence. It's the way they're typed out. Don't try and learn A plus B makes Ca plus Cb. I could easily flip it around. Questions so far? So the rule with that is that the stronger the acid, the weaker the conjugate base. So we'll get more into what strength means numerically later, but a strong acid makes a weak conjugate base, and vice versa. So now I want you to, or you all, to look at these two down here. And for these two reactions, label acid, base, conjugate acid, and conjugate base really quickly. So when you finish, check it against mine. So NH3 is the base, water is the acid, NH4 plus is the conjugate acid, hydroxide is the conjugate base. And the last one we already did. That was my example I wrote out. So acid plus base makes conjugate acid plus conjugate base. So if I give you sulfuric acid, can you pretty much assume this is going to be either an acid or a base? It's probably going to be an acid, right? But here, on this one, water acted as a what? Acid. So when water acts as an acid, what does water turn into? Hydroxide. It gives away a proton and becomes hydroxide. Here, water acted as a what? Base. So when water gains a proton, it becomes hydronium. How did I know what water was going to be? You look at the equation, see what it makes, right? Or you can look at the other reactant. So is there a rule about water always being an acid or always being a base? No. We have a word for that. The word is amphoteric. So if something is amphoteric, it can be an acid and donate a proton, or a base and gain a proton. And we typically decide which one is going to be based on what it's paired with. So let's look at NaOH plus H2O and HCl plus H2O. Can I pretty definitively say that and that is either going to be an acid or a base? Yeah. What's a metal hydroxide going to be? A base. What's hydrochloric acid going to be? An acid. So in that situation, with sodium hydroxide, that means water is going to be the acid. In this situation, water is going to be the base. So in this example, water will become what? Hydroxide. It's going to give away a hydrogen and become OH minus. In this situation, water is going to become hydronium. Okay. Let's look at another one. Let's look at HSO4 -1. Could I describe HSO4 -1? What's its name, by the way?
Sulfuric acid.
It's a polyatomic ion, you learned.
Bisulfate.
Bisulfate. So, you memorized it a long time ago. You should have. Is bisulfate amphoteric? Could I use that label to describe it? Can it both accept or donate a hydrogen? Yeah. So let's say it acts as a base. If it acts as a base, what does it turn into? Sulfuric acid. Okay. If it acts as an acid, what does it turn into? Sulfate. So if I just give you HSO4 -1 and ask you to label it as acid or base, can you do that? No. No. If I give you what it's paired with, could you then label it acid or base? Yes, you have to know what it's paired with. What it's paired with determines how it reacts. And the word we use for that is, how you say it? Amphoteric. It's two big words, phenolphthalein and amphoteric. Okay? Questions about that? Good. So now, a couple of other words we use to describe acids. So we describe acids as either being monoprotic or polyprotic. What do you think monoprotic means? One proton. So what's an example of a monoprotic acid? What? Hydrochloric acid. HCl, nitric acid, HNO3. And I could list several more. So then polyprotic acids have two major categories we typically see. You'll see diprotic and triprotic acids. So what is an example of a diprotic acid? Sulfuric acid. You also see carbonic acid, H2CO3. So then for triprotic acids, there's really just one common example. What's the common example of a triprotic acid? Phosphoric acid. And this one's pretty commonly missed. What is acetic acid? So first, what is the formula for acetic acid? HC2H3O2. So is it monoprotic or polyprotic? It's monoprotic. Does it have more than one hydrogen? Yes. But this is a description of the number of donatable hydrogens. And it just has one that it's going to give away. So it is a monoprotic acid. It has one H out front, if you want to think about it like that. So now, let's think about putting hydrochloric acid in water. When you put hydrochloric acid in water, what they're going to do? Ionize. That's all it can do, right? It has H and Cl, they split apart. There's nothing further that can happen other than the reverse reaction. If you put sulfuric acid in water, it's going to ionize as well. But how many times can it ionize? How many hydrogens can it lose? 2. So there are 2 steps written out here. Sulfuric acid plus water makes H3O plus bisulfate. Could the reaction then just go back that way to the reactants? Yeah. But could bisulfate then continue to ionize and become sulfate plus hydronium? Yeah. So we have a 2-stage ionization, or 2 steps. So for those, go ahead and label acid, base, conjugate acid, conjugate base. That's always goes so much faster in the morning. Any more questions? Any on that? Guess we're just wondering if that's a good thing or a bad thing. We got off on parakeet story this morning. Who's parakeet?
What's your story behind it? I don't
So they found a parakeet out in the courtyard. It's a little like random green bird. And then they caught it and it was in a bird cage in the office. I'll show you a picture of it in a
Where's
minute.
that kind of birdcage chilling in the mountain?
Yeah, I don't know where the bird cage came from. Yeah, that kind of surprised me. So here we have the acid plus the base makes the conjugate acid plus the conjugate base. But in the second ionization, bisulfate acts as the acid. So again, we've already said bisulfate is amphoteric. It can act as an acid or it can act as a base. So if this is at equilibrium, let's say some of the sulfuric acid becomes bisulfate, and then some of that bisulfate becomes sulfate. So there's multiple steps to the reaction, what to think about it. So if hydrochloric acid has a 1-step ionization, sulfuric acid has a 2-step ionization, phosphoric acid has a how many step ionization? 3. So go ahead and write it out, and then label acid base, conjugate base. Okay, so how many steps should you have? 3 total reactions. for the ionization of phosphoric acid in water? You ready? I'll bring it out there. Just stay out there.
We can say something funny on the recording. He said it's second. It's not look at it.
So when you're done, you can look up and check against mine. And obviously your order can change. You can flip the order of the products and reactants. So now we have a multi-stage equilibrium. Some phosphoric acid becomes H2PO4. Some of that becomes HPO4. Then some of that becomes PO4 negative 3. So it's a multiple step process where some molecules get stuck along the way. They stay there because of equilibrium. And we're going to spend quite a bit of time talking about the calculations for figuring out how much does step 1, how much does step 2, and how much goes all the way to step 3. That's a lot of what this math is. And then I labeled the acids, the bases, the conjugate acids, and the conjugate bases. So there are several things I could describe as amphoteric here. I could describe water, H2PO4, HPO4. They can all act as either acids or bases. And one thing I forgot to say yesterday in this class, if you look back at the reactions here, we said that carbonates or hydrogen carbonates or bicarbonates react with acids to make CO2 plus water. What is sodium bicarbonate? My name? Baking soda. Okay. So what is acetic acid? Vinegar. Okay. So carbonate or bicarbonate plus an acid is going to make CO2, which is a solid liquid gas. Yes. So when you mix baking soda and vinegar, what do you get? Bubbles in your elementary school volcano. So that's the reaction for it. Okay, so we see that if you mix those two together. Okay. Any questions about the ionization? Good, so that's as far as we got in first period, so we'll stop there for today.